Episode 4 on cyclic geometry. This is the third theorem, angles on the same segment. Our third theorem. First theorem, we were looking on angles at the center being twice the angle at the circumference. Second theorem, we looked at the angle in a semicircle, or rather the angle subtended by a diameter being 90 degrees. Now our third theorem, its angles on the same segment. What is this segment? Now a segment, this is nothing but a region of a circle separated by a chord. What does this mean? If I can draw a circle and then on this circle I just draw a chord randomly. This is a chord on a circle. The chord is going to divide the circle into two parts. This part and this one here. Now the two parts that are formed by dividing the circle using the chord are called segments. So when a chord is drawn, it cuts the circle into two parts, and those parts are the segments. So basically that's the segment. Now let's check the rule. What does this say? It says the angle subtended by a chord at the circumference. It's subtended by a chord, or sometimes we can say by an arc. So the angle subtended by a chord or an arc at the circumference is always the same whenever it is on the same segment of the circle. The angle subtended by a chord at the circumference is always the same whenever it is on the same segment of the circle. Now, let's check this thing. Let's go straight to GeoGebra to view these angles. Now here is our GeoGebra. Here we have an angle T and angle C. What's happening here? Nice one. If we look at this angle here, angle T, and then also look at angle C there. They are both equal because there is a chord here, AB. This is a chord which separates this circle into two parts, the part on top and the part on the bottom. Now our two angles are on one side of the chord, which means they are on the same segment. So these angles are equal because at this point this angle is connected to both ends of the diameter, which is here and then also here. Same applies to angle C. It is connected to both ends of the chord AB, this point here and that point. So since these angles are connected to the same chord, we are saying this chord subtends them. So the angles subtended by the same chords on the circumference, they are equal. So these angles are equals for as long as these angles are on the same segment. I hope you can see. For as long as the angles are on the same segment, they are just equal. They are just equal. What happens if I bring it on the other segment? Hey, it's changing. It's no longer 65. Let me measure the one. Okay, it doesn't matter. Now this one, it's no longer that. They are now not on the same segment. But for as long as these two angles are on the same segment, they are going to be equal. They are just going to be equal for as long as they are on the same segment. Now, why is this true? Maybe let's look at how we can prove this theorem using some algebra. How can we prove this theorem? Why is it true? Why are the angles on the same segment subtended by the same chord equal? Let's look to how can we prove this one. Why this happens? All the angles are looking at the same chord. From the same side of the circle. Because they cut the same arc, the angles must be equal. Now let's try to prove this one by some small constructions here. We are going to first join AO and also OA. Now from there, let's say the angle at the center is just 2x. Now if this is the angle at the center, this one should be the angle on the circumference. And then the angle at the center we know is twice the angle on the circumference. So this angle at D should be x. Same applies to angle C. If this is the angle at the center being 2x, the angle at C should be x. Now this is x. And just like that, these two angles are equal. And then we have proved that the angles subtended by the same arc. In this case, we don't see a chord here. It's the arc that is subtending these angles. So they are equal. Now let's move on to examples. Example number 1. What does example number 1 says? We are required to find angle X, Y, Z. Now, to find angle X, we are going to use the theorem angle at the center being twice the angle on the circumference. Now, what's the angle at the center? The angle at the center is 86. Then the angle on the circumference is x. So 86 is equals to 2 times the angle at the circumference, which is x, dividing by 2 on both sides of the equation, you are going to get that your x is equals to 43. Now, if this is 43 degrees, since arc LM, or rather chord LM, is common, we can say that this angle is equals to that, being equals to that one too. So angle x is equals to angle y equals to angle z equals to 43. What's the reason for them being equals? These are angles on the same segment. Next example, it's this one here. Example 2, we are required to find the value of angle x. Now let's go to x, to which angle is angle x on the same segment with. Which two angles are being subtended by the same chord with the angle x? Let's check that. So to check that, where is our common chord? Now this is our common chord. Now this chord, if you join the lines arising from the same chord, you are getting this angle here, which is angle x. At the same time, you are also getting this angle there, which is angle C. Now, both these angles are subtended by the same chord, this one there. So, we are expecting that this angle is equals to that angle. Angles on the same chord, they are just equal. Now this simply tells us that this is nothing but x. Now how do we find the value of x? Let's look at this one closely. Now looking at this one closely, let me draw another line here so that we have that triangle there, which is red. BC passes through the center. What does that tell us about BC? If BC passes through the center and both its ends are on the circumference of the circle, BC should be a diameter. BC is a diameter. If we know that BC is a diameter, therefore the angle subtended by BC must be 90 degrees. What's that angle? It's EGCSE. This angle there. It must be 90. It is actually 90 degrees. We've already established that using angles in a semicircle. So what do we say here? Angle BGC is equals to 90 degrees. The reason, this is angle in semicircle. Now, if this is 90, this is 30, then we can easily find x using the sum of interior angles in a triangle. Now, how do we find x? So 30 plus 90 plus x, this should give me 180. Now 30 plus 90, it's 120 plus x, this is equals to 180. Then let's subtract 120 on both sides of the equation. Subtracting 120 on both sides, this 120 is going to be cancelled out by this one, so that on the left hand side we are left with just x being equals to 180 minus 120. It's actually 60 degrees, which is the value of x. Now let's move on to the next example here. Now for this example, we are told that PQRS are points on a circle. Are points on a circle, or if you like and say they are points on the circumference of a circle, and then the center is O. QS is a diameter. QS is a diameter. If QS is a diameter, already this angle should be 90 degrees. Simply because this is a diameter. Now angle PRS is 42 and PQ is 5.9. We are required to calculate the circumference of the circle. So for us to be able to calculate the circumference of a circle, we need the diameter, because circumference is 2 pi r. So how do we find the diameter? The radius. Now let's use our law. Angles on the same segment, which is the chord dividing the circle into two segments. It's called SP. Now, which are the two angles that are on the same segment? This angle together with these ones, they are angles on the same segment and subtended by the same chord SP, which means those two angles are equal. Then we have what here? 42. Now let's just write it, put it down in writing. Angle S R P is equals to angle S Q P equals to 42 degrees. The reason for this, angles on same segment. Then from there, we noticed that QS is a diameter, which simply means that angle SPQ is equals to 90 degrees, because it's an angle in a semicircle. Then now we have what? We now are having a side together with an angle in a right angled triangle. What are we looking for? We are looking for the side. So to find a side, given the side and an angle in a right angle triangle, you just use your SOHCAHTOA. Let's use our SOHCAHTOA here. So from SOHCAHTOA, SOHCAHTOA. Let's identify the stuff that is given there. What stuff is given? In the triangle, we have an angle there. What's the angle? 42 degrees. And then in relation to the angle, we have this side, which is 5.9, is adjacent side. Adjacent, it's 5.9. Then we are looking for the hypotenuse. And then the hypotenuse is actually x. Now this is A. And then this is H. Now AH. Which among these has an AH? It's actually this one here. So we are going to use what? The first letter here, it's C, which simply means that we must use cos. So our cos of the angle 42 is equals to the adjacent, it's 5.9, divided by the hypotenuse, it's x. If you multiply by x on both sides, you are going to get x cos 42 is equals to 5.9. Divide both sides by cos 42, you are getting that your x is equals to 5.9 over cos 42. Now let's take this into our calculator. Now putting this in a calculator, we get x is equals to 7.93923, and then this is an irrational number. Let's just leave it like that. Now this is the diameter, so the radius must be equals to half of this. Now if you take half of that, you are getting that the radius is equals to 3.96916. It's an irrational number. Let's leave it like that. Then the circumference of the circle C is equals to 2 times pi times r. So your C is equals to 2 times pi. It's 3.142. It's an irrational number, this one, multiplied by the 3.96916. Now what are we getting for this? On your calculator, just press 2 pi, then answer, and then it's going to give you 24.9413. 8, 3, 6, 3, 9, 6, 7, 9. Then let's round off this one to 3 significant figures. So the circumference is equals to 24.9 centimeters. And that's it for this lesson. Don't forget, our lesson was on the theorem on angles on the same segment, which says that angles on the same segment are equal. The angle subtended by a chord or an arc at the circumference is always the same whenever it is on the same segment. The angle is subtended by a chord or an arc at the circumference are equal whenever they are on the same segment of the cycle. And that's the theorem. Thank you for staying tuned.